Hi, I'm Ian Cunningham from VectorGB. Welcome to this episode of Engineering the Jigsaw, Foundation Episode 3, all about networks in vehicles. So in today's episode, no surprise, we're going to be talking about networks in vehicles, and these are a major factor in Vector's business. They really are the foundation of Vector as a business as it is today. Vector does more things than just things to do with networking, but if we go back 20 or 30 years in Vector's history, it was the primary thing Vector was involved in. So we will, in today's episode, be talking about some ideas that referring to some ideas that we covered in episode F1, a 50,000 piece jigsaw puzzle. So if you haven't seen that, I highly recommend you watch it before today. And also, you may find it useful to have watched episode F2, what is an ECU? So why? Why do we put networks in vehicles? Well, while linking ECUs up together inside the vehicles might give us new possibilities in our functions that we have in vehicles, we might just do this by throwing more wires in. And in the 1980s, it was realized that networks meant that vehicles could use fewer wires, and fewer wires is good because otherwise wiring might start to become difficult to actually put into vehicles. So, well, why? Well, let's look at some wire. Here's some wire. Automotive wire, 0.5 millimeters squared automotive FLRI wire. That's the standard kind of wire you'll find in most vehicle wiring. You get some that's quite a bit bigger for power, but this is kind of standard stuff for wiring up all those sensors and actuators and stuff we've talked about in the past. And also, quite often, can be used in communication buses, communication networks. So, so one wire on its own, it doesn't look like a problem, does it? But if we start to double it up, I've got a big length of it here, so 2 wires, still not a problem. That's that's 4 wires, that's 8 wires, and that is 16 wires. I'll give it a bit of a twist just to help you see. So that's kind of starting to approach the size of my little finger maybe in diameter. And if I double it over again to get to 32, we can see it's, give it another little twist. It's really starting to take up some space now. Every time I fold it in half twice, so every time I quadruple the number of wires, I'm doubling the area. So that is 32 wires. In the past, we talked in a previous episode about 15,000 signals being in a modern day vehicle. So imagine trying to have a bundle with 15,000 wires, and that bundle would have to go between nearly all of the 100 ECUs that go into the vehicle. Probably not achievable. That's today's prop done with. And of course, each wire we put in adds cost and weight because they're not short like my little bundles here. They're going around the whole vehicle. So if it's a car, it could be 5 meter, 6 meter wires. If you've got a truck or a bus, you could be looking at 10, 20 meters long wires. So lots of cost and weight you can add in very quickly just by adding in additional wires if you don't need to. So, and networks, of course, and network protocols allow ECUs to share data both quickly and precisely with a reduced risk of undetected errors. And this is really important because the ignition systems that are in combustion engines, which of course were common in cars in the 1980s, we're starting to see a transition away from them nowadays. Well, ignition systems create a lot of electrical interference, which can interfere with sensitive electronics. And this meant that you need to have special network technologies to use in vehicles to be robust against that kind of interference. What do we mean by this interference though? Well, you may know you've listened to a radio in the past in the middle of an electrical storm, FM or AM radio, and you've heard popping as the lightning's going. Well, that's the interference. And inside a spark ignition engine, you've got effectively thousands of little artificial lightning bolts every second. So all that popping would be stuff that would be going into the wiring possibly. So we don't want that. We try to engineer that out. And use of digital signaling means that we can detect and also correct these kind of things automatically, even in some cases. And detecting something going wrong is great because it means we can then make a decision about what to do with that thing when we know it's not right. We can choose to ignore it, or we can choose to do some special action when we lose a source of data. But if we don't know there's a problem with that source of data, we can be in real trouble. So if we were just varying a voltage and then a problem in the wiring or some interference was causing that voltage to vary, that varying voltage would look to us like what we were measuring was varying, and we'd then do whatever that meant we had to do in our logic and our ECUs. That's just how they work. They're relatively dumb. They follow the inputs, and they do the outputs as programmed. So we have this digital signaling. How does it actually work? Well, networks used in ECU between ECUs in vehicles within the EE systems use something called serial communications. I'm doing serial communications with you right now. Speech is a form of serial communication. Serial communication just means that we have a single stream, one thing at a time. So I can't say three things at exactly the same moment. And with serial communications, we can only send one thing at a time. So we talked in episode F1 about traction control, where our car starts to spin its wheels and the ABS module, ECU, detects this and then says to the engine ECU, please reduce power. And this is how we get traction control. We detect the wheels are slipping and we ask the engine to reduce its power. Of course, it doesn't just do this. It might then also send the speed, current vehicle speed, to the engine. And then, of course, it will say something like stop producing power. So it does these in a sequence, effectively cyclically, one at a time on the network. And how we actually realize this at the level of the ECU is we have a sequence of voltages applied to the wires that make up the network. And we have defined voltage levels that correspond with the value of a binary digit, or bit for short. So we have a value that corresponds, a voltage, I should say, that corresponds with a value of 0, and a voltage that corresponds with a value of 1. Sometimes, not always, but sometimes. This is an easy way to understand it. So we have this varying voltage, and if it's at a particular level, it means a 1, another 1, it means a 0. So we get a flow of zeros and ones, and zeros and ones are numbers. And as we've talked about before, numbers are what is used by software. So our software can interpret this, get its data that it needs to operate, and then do what it needs to do. And the speed of communication is frequently measured when we talk about networks in terms of the number of bits that are able to be sent per second, or bits per second, BPS. Different network types have come in over time to introduce new needs and meet new needs. And it's true to say that most vehicles use most of them. It's not that one vehicle will use one network of one type. It will have many networks of different types in it in most cases. So where did we start? Well, we started with the kind of need for speed, precision, quickly sharing data, and of course good value always in the background. And CAN, Controller Area Network Bus. This was specifically developed in the early 1980s to meet the needs of vehicles with a speed of up to 1 million bits per second, 1 megabit per second. Mega is million. So relatively fast, you'd think, fairly fast. Okay, maybe not as fast as a modern network in an office or something like this, but yeah, it seems fast. And of course, CAN started to be used. The first vehicle with CAN actually in it was produced in the very early 1990s, and CAN is abundant today. So it's gone way outside the automotive industry. So it's in trucks, buses, planes, cars, ships, laundry machines, robots in factories, satellites up in space, you name it. CAN is everywhere. Chances are you've been near something today that has CAN inside it as a technology, helping it to do whatever it is that it does. But in the late 1990s, it was realized that CAN was a little bit too expensive just to be used all the time. So, and in common with many other things, fast things tend to cost more than slow things. So fast cars, fast motorbikes, fast boats tend to cost more than the slow equivalent. So people started to look and develop a lower speed, lower cost alternative to CAN, which is they called LIN, Local Interconnect Network. And this runs at a speed of around 20 kilobits per second. Kilo, of course, is the prefix we use for 1000. And it was also realised that around the same time, actually, as people started thinking about LIN, that CAN couldn't actually meet all the needs we have in vehicles. So some systems run at very high speed and have very tight timing requirements. They really need to operate at the exact moment an input happens. So if that input is happening remotely, that needs to be transferred immediately or very predictably to the places that need to use that. And something called FlexRay was developed, and this gave a fault-tolerant, higher speed, 10 megabit per second network. You can actually get 20 megabits per second with FlexRay. If you do some jiggery-pokery, you can run 2 channels in parallel and effectively double the amount of data you can send. In general, 10 megabits per second. And we haven't stopped there. This is still the mid-2000s I'm talking about in the time frame here. So let's get up to the modern day. Ethernet. We're now starting to see Ethernet in vehicles. You may know Ethernet from your home network or your office network. There's an Ethernet cable. That's not the kind of Ethernet we have in cars. It's slightly different, but you are roughly familiar with it. Ethernet came into vehicles to begin with to carry video and audio data in the entertainment system. So Ethernet in vehicles typically runs around 100 megabits per second. ADAS systems use video. They also use LiDAR data. They use radar data. Loads and loads and loads of data they need to send every second. So those ADAS systems, those advanced driver assistance systems, also make use of Ethernet quite commonly. And Ethernet actually allows you to do other things. So the technologies we talked about, CAN, LIN, FlexRay, they're signal oriented. So things like the vehicle speed or requests to reduce torque, they're a signal. So effectively what that means is it's kind of sent whether anybody wants it or not out onto the network, and then anybody that wants to kind of tap in can pick it up. Ethernet allows a concept called service-oriented architectures to work, and what this means is that people or ECUs that need data are able to request that data from something that is able to provide it. So it's more like an ad hoc style of networking rather than everything being predefined. So it means we can add functions into vehicles more easily, which obviously lots of people nowadays are looking at software over the air updates in cars. So service-orientated architectures play a role there. And most modern IT systems are based on service-orientated architectures. And so this means that some ECUs can now speak the same language as the servers used in data center, which creates even more possibilities. So in this episode, we've looked at why networks are used in vehicles and how they typically work. I've also talked about the different network technologies and why they were developed, and that they're often in many other places. And as I said, it's not the case that a car will have, or a truck or a bus or whatever will have a single CAN network. It will probably have 5 or 6 CAN networks. It might also have a few Ethernet networks in there, a number of LIN networks linking up to things like switches and wiper motors as well. So there's loads of networks in a modern vehicle. They're linked up together by special ECUs that are called gateways that select data to take from one network and put it onto the other. We've touched on that, really the very newest network technology that's come into vehicles of Ethernet and hinted at some of the things that can do. I just mentioned a modern vehicle system can contain many different networks, all operating at the same time and sharing data around. And advances in technology mean now that some ECUs communicate beyond the vehicle, for example, with servers in data centers. If you want to know more about networks in vehicles, it's a huge topic. We have free training available via our e-learning portal for CAN, LIN, FlexRay and Ethernet. That's there. Links in the description where you find this video. And of course, there are loads of details on our website, in our technical articles and in our webinars on all the products that Vector provides for design, development, analysis, simulation, calibration, diagnostics and testing of ECUs and communications in vehicles and between vehicles and the wider world. Like I said, it's really fundamental to Vector. So almost everything you'll find on our website has some relationship to that kind of communication in vehicles. And of course, we also provide the software for the ECUs that allows them to communicate over those different network technologies. And we also provide the software that allows ECUs to work with off-board systems to do over-the-air updates and those kind of things. Besides all that kind of normal communication, we have these kind of special cases like updates, but also diagnostics and calibration. So do make sure to join us for our next planned episodes, which are on what is diagnostics and what is calibration. In the meantime, if there's any topics you'd like to know more about, please don't hesitate to get in touch with us. Please email us using our special email address, which is engineering.jigsaw@vector.com. I'm Ian Cunningham. Thank you very much for joining me. See you soon.